It is the late 1800s, and the science of light measurement is beginning to be taken very seriously. And it is the humble candle that lights the way. One candle in particular shines most brightly in this sea of waxy radiation, the spermaceti candle. Made from the waxy substance found in the craniums of sperm whales, the bright, clean-burning spermaceti candle becomes the gold standard in light measurement. It was Victorian science at its finest, a particular weight of candle burning over a prescribed period of time and producing a set amount of light. Its output was expressed quite literally as candle power. And while this measurement seems unscientific by modern standards, the definitions and units of light measurement used today are still closely linked to our flickering friend. Unfortunately, the harvesting of Cretaceous wax and other oils doomed the poor sperm whale to 2 centuries of slaughter. A better way had to be found. In 1881, the French physicist Jules Violle proposed a new standard of light source, which was unsurprisingly called the viol. Based on the light produced by 1 square centimetre of platinum heated to its melting point, the light emitted was the equivalent of approximately 60 standard candles. By the 1940s, it was decided to value the viol closer to candle power, dividing it by 60, and in 1948, this new standard unit of light measurement was named the candela. Candle power and candelas are, to all intents and purposes, interchangeable, but while you might still see candle power used to describe focus lights such as flashlights and searchlights, etc., it's an archaic term that has been almost completely replaced by the candela. Candle power and candela are both measurements of intensity, and intensity is described as the measure of light emitted from a source in a given direction, rather than the total output of the source. The more focused a beam, the more intensity of light is produced in a given direction. Lamp manufacturers often provide a map of the distribution of these intensities. You may have seen a diagram similar to this one. It is a graphical representation of the intensity of the light plotted against polar coordinates. The more off angle from the focused light one gets, the weaker the intensity becomes. With 0 degrees being head-on to the lamp, you can see that the maximum beam intensity is between about 10 degrees left and right of center, a little over 1,000 candelas. By the time the light is measured at 45 degrees from center, the intensity is a quarter of the original intensity, about 250 candelas. If intensity is a measurement of light focused in one direction, then flux is a measure of the light a source emits in all directions. It is measured in lumens. As an example, you will often see lumens used to describe the amount of light a household bulb will output. Flux and intensity are related, but are not the same. Imagine a 1 lumen light source that outputs light evenly in all directions and measured in any direction has an intensity of 1 candela. If the focus of the light is then concentrated either by a lens or a reflector, for instance, the resulting intensity for that direction will be greater when measured, but the overall flux will have not changed. We see this with lamps that flood and spot. Even though the intensity of the lamp changes when the beam is made wider or narrower, the actual output of the lamp remains the same. A 2K lamp is still a 2K lamp, whether flooded or spotted. Illuminance is derived from intensity and is a measure of incident light, and by incident we simply mean light hitting a surface. Illuminance is measured in lux, or, as still seen occasionally in photography, foot candles. If we think of intensity as a measure of the cause, then illuminance is a measure of the effect that a light produces. There is a direct relationship between intensity and illuminance. A change in intensity over a constant distance will show a corresponding change in illuminance. If we use foot candles for visual simplicity, 1 candela of intensity at 1 foot equals 1 foot candle of illumination. 2 candelas of intensity at 1 foot equals 2 foot candles of illumination, etc. If we swap things around and keep the intensity constant but change the distance measured, we are introduced to what is known as the inverse square law, a behavior of light that will become one of the pillars of your lighting design. 1 candela of intensity at 1 foot equals 1 foot candle of illumination. 1 candela of intensity at 2 feet equals a quarter of a foot candle of illumination. And why is this? It is because the light fall-off is not in proportion to the distance, but in proportion to the square of the distance. At 2 feet, the light source has to illuminate an area 4 times that of the area at 1 foot. Hence, the light illuminating the area is quarter the intensity. We measure illuminance with an incident meter. An incident meter has either a flat diffuser or a hemispherical diffuser that measures the light falling onto it. While the flat diffuser measures the light falling onto it directly from one source, the hemispherical diffuser is designed for metering a face, with it taking into account incident light from a number of directions. This gives a more balanced reading of different illuminance measurements. Luminance is again derived from intensity measurements, but is related to the light measured at a projected surface. It is expressed as candelas per square inches, or feet, or meters, etc. The concept of luminance applies to reflecting and transmitting surfaces as well as to light sources, since it makes no difference whether the surface being considered is originating the light or reflecting or transmitting the light. Luminance is often described as the photometric equivalent of brightness. But with brightness being a perceptual term, it can be hard to quantify, hence luminance. If we were to measure light falling on a diffuse surface that reflected the light with 100% efficiency, then we could say that the luminance measurement equals the illuminance measurement. This, of course, does not happen in the real world. Whenever a reflected light meter reading is made, it is a luminance measurement. Wandering around with your spot meter, measuring the light bouncing off a table, skin tones, a practical source, a window blind, etc., all of these are examples of luminance measurement. False color and zebra are luminance measurements, and the inverse square law does not apply when measuring luminance. If you take a spot meter reading from 2 feet away or 10 feet away, as long as the surface is even and fills the spot, the reading will be the same. So to summarize, flux is the measure of the total light source emitted and is measured in lumens. Intensity is the measure of light focused in one direction and is measured in candelas. Illuminance is a measurement of intensity and is measured in lux or foot candles. And luminance is a measurement of a source or reflection of light and is measured in candela per square inch, foot, or meter. In the real world of cinematography and photography, it really comes down to thinking of light as either incident or reflective, and metering tools are designed with this approach in mind. While it may seem quite old school to use an incident and spot meter in a world of false color and waveforms, there are some advantages to using the trusty handheld meter. An incident meter allows one to think three-dimensionally. While false color will give you a wealth of information regarding the image on the monitor, there is nothing like wandering around a space and understanding the light coming from all directions. Or if having a T-stop for different lights in your head and knowing how lights read relative to each other in a studio setup. Or even how light on location changes during the day.